contain a set of visited nodes, and then we are going through, starting at some root node, which for us is O. That's where we want to start the topological sort. And starting at O, we go through all of its children, and we need to lay them out from left to right. And basically, this starts at O. If it's not visited, then it marks it as visited, and then it iterates through all of its children and calls build topological on them. And then after it's gone through all the children, it adds itself to the topo list after all of the children have been processed. And that's how this function is guaranteeing that you're only going to be in the list once all your children are in the list. We're going to see that it ordered our value.
हाँ नहीं नहीं वही वीडियो बस खत्म कर रहे थे कल जो देख रहे थे ना। रुक जा कुछ बस 15 मिनट में चलता। 10 बजे तक चलता। हाँ ठीक ठीक। अच्छा हाँ। Uh,
objects. And the last one is the value of 0.707, which is the output. So this is O, and then this is N.
hmm.
N, and then all the other nodes get laid out before it. So that builds the topological graph. And really what we're doing now is we're just calling dot underscore backward on all of the nodes in a topological order. So if we just reset the gradients, they're all 0. What did we do? We started by setting o.grad to be 1. That's the base case. Then we built the topological order.
Not going to topologic. We got the 2 point.
And then we went for node in reversed of topo. Now, in the reverse order, because this list goes from, we need to go through it in reversed order. Should be it. There we go. Those are the correct derivatives. Finally, we are going to hide this functionality. So I'm going to copy this, and we're going to hide it inside the value class because we don't want to have all that code lying around. So instead of an underscore backward, we're now going to define an actual backward. So that backward without the underscore. And that's going to do all the stuff that we just derived. So let me just clean this up a little bit. So we're first going to build a topological graph, start
Chicken graph. In
starting at self. So build topo of self will populate the topological order into the topo list, which is a local variable. Then we set self.grad to be 1. And then for each node in the reversed list, so starting at us and going to all the children, underscore backward. And that should be it. So save, come down here. Here, we define, okay, all the grads are 0. And now what we can do is done backward without the underscore. And there we go. And that's backpropagation. Place for 1 neuron. We shouldn't be too happy with ourselves, actually, because we have a bad bug. And we have not surfaced the bug because of some specific conditions that we have to think about right now. So here's the simplest case that shows the bug. Say I create a single node A, and then I create a B that is A plus A, and then I call it backward. So what's going to happen is A is 3, and then B is A plus A. So there's 2 arrows on top of each other here. Then we can see that B is, of course, the forward pass works. B is just A plus A, which is just 6. But the gradient here is not actually correct, that we calculated automatically. And that's because, of course, just doing calculus in your head, the derivative of b with respect to a should be 2. 1 plus 1. It's not 1. Intuitively, what's happening here, right? So b is the result of a plus a, and then we call backward on it. So let's go up and see what that does. B is a result of addition, so out is b. And then when we call backward, what happened is self.grad was set to 1, and then other.grad was set to 1. But because we're doing a plus a, self and other are actually the exact same object. So we are overriding the gradient. We are setting it to 1, and then we are setting it again to 1. And that's why it stays at 1. So that's a problem. There's another way to see this in a little bit more complicated expression. So here we have a and b, and then d will be the multiplication of the two, and e will be the addition of the two. And then we multiply e times d to get f, and then we call f dot backward. And these gradients, if you check, will be incorrect. So fundamentally what's happening here, again, is basically we're going to see an issue anytime we use a variable more than once. Until now, in these expressions above, every variable is used exactly once, so we didn't see the issue. But here, if a variable is used more than once, what's going to happen during backward pass? We're backpropagating from f to e to d, so far so good, but now e calls it backward, and it deposits its gradients to a and b, but then we come back to d and call backward, and it overwrites those gradients at a and b. So that's obviously a problem. And the solution here, if you look at the multivariate case of the chain rule and its generalization there, the solution there is basically that we have to accumulate these gradients. These gradients add. And so instead of setting those gradients, we can simply do plus equals. We need to accumulate those gradients. Plus equals, plus. We can simply add in there, and it deposits its gradients to a and b, but then we come back to d and call backward, and it overwrites those gradients at a and b. So that's obviously a problem. And the solution here, if you look at the multivariate case of the chain rule and its generalization there, the solution there is basically that we have to accumulate these gradients. These gradients add. And so instead of setting those gradients, we can simply do plus equals. We need to accumulate those gradients. Plus equals, plus equals, plus equals, plus equals. And this will be okay, remember, because we are initializing them at 0. So they start at 0, and then any contribution that flows backwards will simply add. So now if we redefine this one, because the plus equals, this now works. Because a dot grad started at 0, and we call b dot backward, we deposit 1, and then we deposit 1 again, and now this is 2, which is correct. And here, this will also work, and we'll get correct gradients. Because when we call e dot backward, we will deposit the gradients from this branch, and then we get to d dot backward, it will deposit its own gradients. And then those gradients simply add on top of each other. And so we just accumulate those gradients, and that fixes the issue. Okay, now before we move on, let me actually do a bit of cleanup here and delete some of this intermediate work. So we're not going to need any of this now that we've derived all it. We are going to keep this because I want to come back to it. Delete the 10H, delete our motivating example, delete the step, delete this, keep the code that draws, and then delete this example and leave behind only the definition of value. And now let's come back to this nonlinearity here that we implemented to 10H. Now I told you that we could have broken down 10H into its explicit atoms in terms of other expressions if we had the exit function. So if you remember, 10H is defined like this, and